Okay, in this video we're going to do the old 14.2 day 2, also called G2 day 2. So either way, this is what we're going to do. It's the second day of the second set of probability. So it says in today's session we're going to analyze events and search for commonalities. This will lead into a discussion of the probability of OR. So OR is here. Hang on one sec. Or, so if you're going to say or, if you say that in set notation, it looks like a U, and looks like an upside down U. Events as well as the relationship between an event and the event that follows it. Okay, there are 10 balls in a bag. They are numbered from 1 to 10. You reach into the bag, pull out one ball, and note the number on the ball. Calculate the probability. See, the second you see probability, you're going to be thinking fraction for each of the events listed below. Your number is a 3. Well, there are 10 balls, and they're numbered 1 to 10 with no repeats. So therefore, 1 out of 10 times, you would get a 3. Same for the next. The number is 4. The probability of that is also 1 out of 10 times. Okay, your number is a 3 or a 4. Okay, so you're going to say the probability of a 3 plus the probability of 4 minus the probability of a 3 and a 4, which is going to be 0. Okay, so this is 0. This is 1/10 plus 1/10, and your answer is going to be 2/10. Now this will make more sense in the next example. Okay, your number is even. So even is going to be 2, 4, 6, 8, or 10. So 1, 2, 3, 4, 5 times, you're going to get an even. Your number is divisible by 6. Well, only the 6 is divisible by 6. So 1 out of 10 times. So 1 out of 10 times, will you get a number divisible by 6? Because I had to re-evaluate all of my numbers again. And when they say divisible, they mean evenly. Okay, there's no other number besides 6 that's divisible by 6. Okay, your number is even or divisible by 6. So that means you're going to say probability of even plus probability divisible by 6 minus the probability of even and divisible by 6. Okay, so probability of even was 5 out of 10. Probability divisible by 6 is just 1 out of 10. Minus, so then minus 1 out of 10. We can't double count, and that's going to give me 5 out of 10. So we are avoiding, so by doing that subtraction, we avoid double counting. Okay, so really our equation is, let me write this up here. If I want to figure out the probability of, let's see, 3, and then it said your number is this or that, so 3 or 4, oops, sorry, or 4, that equals probability of 3 plus probability of 4 minus the probability of 3 and 4. That's what we're doing, okay? So if you want to figure out an or, you're going to have to eliminate any ands because otherwise you would double count. Okay, so I hope that explains that. We're going to do more with this in just a few minutes. Okay, For example, it's A and B above, add the probability numbers you received for the first two pieces and compare it against the probability value that you received for the OR event. Okay, so what did you notice about the first comparison? That's the 3 and the 4. You have no common element. What you notice about the second comparison? That's when you have an overlap. Overlap or common element occurs. Why are we seeing different results in these two comparisons? Well, you're seeing different results because of the commonality. And so when there's a commonality, you need to subtract the and part of it. Okay? So I'm going to say if and exists, subtract it away. Okay. For example B, what's the probability that your number is even and divisible by 6? So for that, it's an and. So that's probability of even and divisible by 6. That was the 1 out of 10 that we had to subtract away when we were trying to solve an OR problem. Okay, when we're trying to solve an AND problem, we're only going to tell that number. If events A and B have no common elements, then the probability of A or B can be attained by simply adding probability of A and probability of B. Okay, so let's get an equation for that. If I have probability of A or B, so which one's the OR? This is the OR. That's going to equal probability of A plus the probability of B if no overlap. Okay, however, if A and B share some common elements, then we must account for that overlap in order to calculate probability of A or B. So, look what we have to do. This is our new equation. If I know there's an overlap, then I have to subtract away the probability of A and B. Okay, that is your overlap. If your overlap is 0, there's no need to think about it. All right, so let's keep going. So here comes the notation that I've been doing, but now we're going to do it formally. So it says union probability and mutually exclusive / non-exclusive events. Okay, so if A and B are two events, then the probability of A or B is written probability A, U, B. If probability of A and B instead is written probability of A upside down U, B. Okay, so this is and you can think about the N in and looking like that upside down U, and this is OR. Okay, picking a card, and you can think about that U, if you fill it in the top, it's going to be O as an OR. Picking a card, okay, so this is important, picking a card from a standard deck of 52 cards. So we have gone through the cards already, but here's your standard deck. Here's our inclusive event. Events that have a common intersection. This is our equation. If they're mutually exclusive, then they have no common intersection, and we can use this. Okay, let's practice. Using your playing card diagram where you drew one card from 52, find, okay, the probability of heart or 8. So the probability of a heart, I have 13 hearts. Remember, I'm just picking one card. Plus I have, let's see, I have 4 8s. So 4 out of 52. And then a heart and an 8. What do you think? Is that mutually exclusive or not? No, you can have a heart and an 8. So that's the 1 over 52. So that's going to give me not 17 over 52. If I said 17, I'd be double counting. I'm going to end up with 16 out of 52. And it's because this is the intersection. That's what they have in common. Okay, let's look at the example under the mutually exclusive. What's the probability of getting a red or the ace of spades? Okay, so red or ace of spades equals probability of red. Okay, so there are red cards that are diamonds and red cards that are hearts. So that's 26 over 52 plus the ace of spades is only one of those. The ace of spades is a black card. Black cards and red cards do not overlap. So there is no overlap. If you want, you can say minus 0 over 52 just to reinforce the fact that you thought about it. Or you can just say 27 over 52 and you're good. Okay, let's keep going. What's the probability of getting a jack or not a spade? Okay, so that's interesting. So these are complements. When you say not a spade, I want you to think complement. Okay, this is complement. Okay, probability of jacks. Let's think about that. There's a jack in every suit, so that's 4 out of 52. Plus the probability of not a spade. Okay, so there are 13 over 52 spades, so not a spade has to be 39 over 52. Minus, isn't it true that you could have a jack and not a spade? So there's jacks of hearts, diamonds, and clubs, so that's 3. So here's the intersectionality right there, and we're going to make sure that we subtract that away. So that's going to end up being, what, 40. Right? So if I have that, yeah, 40. So 40 over 52. Okay, let's look at the next one. This one says, what's the probability of getting, when you're picking this one card, of getting a 2 or a queen? So are there any 2s that are queens? Of course not. So there's 0 there. So there are 4 2s, one in every suit. So that's 4 over 52. There are also 4 queens. And you get 8 over 52 with no commonality. Okay, so when there are no commonality, these are mutually exclusive. You can't be both a 2 and a queen, and you can't be both a red and an ace of spades. Okay, so that's what's mutually exclusive. When they are not mutually exclusive, you need to subtract away. So here's one more that falls under the not mutually exclusive. So what's the probability of getting a club or a face card? So there are, 13 clubs, so 13 over 52. There are 12 face cards, and there are 4 face cards that are also clubs. So that's going to end up giving me 21 out of 52, because that was an example that was not mutually exclusive. Okay, so again, we're picking one card. Okay, so then, now you have an intersection probability and dependent independent events. If you know that event A happened, does this change the probability of event B happening next? So these events are happening in a row. Okay? So let's look at this. The outcome of the first event, if it affects the outcome of the second event, this is your situation. So what is this downward U? Do you remember? It's the and, right? So the probability of A and B is the probability of A, and then the probability times the probability of B, because you've got events in a row, so you're multiplying. Okay, we're back to multiplying. How come we were adding here? Picking a card, you're picking one card. Okay, using the playing card, a heart and an 8. Okay, you're picking one card is happening all at once, whereas here you are picking in sequence. Okay, so you want to understand that if you pick in sequence, you're going to multiply the events because there's more than one event. Here, there's only one event you are adding. So why don't we write that up here? If you have one event, you're going to add. If you have sequential events, you are going to multiply. Okay, this is a point of confusion, so that's why I stopped to do that. So notice this notation. We are familiar with probability of A, but this says probability of B given that A has already happened. Okay, so let's think about this. Here's our scenario. Now we have dependent events. That's telling me that the second event is dependent on the first event that's already happened. Okay, a jar contains 10 slips of paper numbered 1 through 10. 2 slips are randomly pulled from the jar, one at a time. What's the probability of choosing the 5 followed by the 8? Okay, so there are 10 slips of paper. So I reach in, I grab a 5. I have a 1 in 10 chances of grabbing that 5. I do not return the piece of paper that I pulled that had the 5. I keep it out. Then I reach in and pick again. I have a 1. There's 1 8 in there, but there's only 9 pieces of paper left because I left 1 out. So that's 1 over 90 and not 1 over 100. Okay, the fact that you've already picked a number out of the bag or out of the box or out of the jar and don't put it back has an impact on the divisor of the second event. Okay, number 3, let's look at that. So this is another situation where you have dependent. So it says, what's the probability of choosing an odd number followed by an even number? Okay, so there, if the numbers are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so here are your evens, 2, 4, 6, 8, 10. There are 5 evens and there are 5 odds. Okay, so what's the probability of choosing an odd number followed by an even? So you pick, and you have a 5 in 10 chance of getting an odd. Now you pick again, and you have a 5 in not 10, but 9 chance because you didn't put back the paper that you pulled the first time. So this is without replacement. Okay, and they're dependent events. Okay, so the outcome of the first event in the independent does not affect the outcome of the second event. Okay, so let's look at that. Okay, here's our notation. Notice that this just says probability of B. It doesn't say probability of B given A because they've already told us that the events are independent. So here's a scenario. A coin is flipped successively. That means in a row. For 2 coin flips, what's the probability of 2 tails? Okay, so the first, you flip it, you have a 1 out of 2 chance of having a tail. You take that same coin and flip it again. The first event does not have an impact on the second event. So the probability of those 2 coins being tails is 1/4. Okay, what if you have 4 coins? What's the probability of 4 heads? Well, each one is going to be 1/2. Okay, so be careful here. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. Don't get 8. Okay, it's not going to be 8 in the denominator. Okay, mutually exclusive. That's how I do it. So before you start a problem, ask yourself here, did what happened before change what may happen next? Okay, this should be easy. This is the last thing we're doing in this section. But some people find this difficult. So let's see if we can make sure that we understand this. In 2014, 5,000 international students enrolled in Maryland universities were surveyed to determine country of origin. The results are displayed in the table below. Okay, big picture. You have 5,000 students. They are all international, and these are the countries that they come from, and these are the universities in Maryland that they attend. Okay? So you want to understand what you're looking at first. If one of these students was chosen at random, what is the probability that the student chosen is a Japanese student at UMBC? Okay, so it looks to me like for Japanese students, maybe we'll do this in red. Here are the number of students at UMBC, and 5,000 is the total number of students. So if you're going to choose one of these students, you have a 272 out of 5,000 chance that that student is a Japanese student at UMBC. Okay? Okay, what's the probability that a student chosen is at UMBC? So now you have to figure out how many students are at UMBC. Look at UMBC and go down to the 516. That's how many students are there. Out of the 5,000, 516 are at UMBC. Okay, look at this one. A Japanese student, the student is Japanese or at UMBC. Okay, so probability of Japanese plus probability at UMBC. Now, can there be an overlap? Oh, yes. Minus the probability Japanese and UMBC. So what's the probability of Japanese? There are 2791 Japanese. So it's 2791 over 5,000 plus the probability of UMBC. There are 516, right, over 5,000. And now you have an overlap. There are some students who are Japanese and they're at UMBC. So you have counted them twice. That's the intersection. So you're going to subtract away that intersection. And you get 3035 5,000. Okay, think about that. Okay, because that was not mutually exclusive. Okay, so we were trying to figure out probability of A and, or B. Okay, now we have probability of Nigerian or, oh, here, let me change one little thing. That should be the other way. Let me do that real fast. So this was Japanese or is up, UMBC. Okay, probability of Nigerian or U is up, probability of Saudi Arabian. Okay, is there any overlap? Could you be Saudi Arabian and Nigerian? So according to this, they only asked them for one nationality, so they cannot be both. So let me turn to brown. No, let me turn to blue. Yeah, blue's okay. Okay, so probability of Nigerian, go across. And don't forget it's probability, so you have to put it over the 5,000. Plus probability of Saudi Arabian, and that's here. So that's 254 over 5,000. And that's going to end up being 542 over 5,000. Okay, last question. An international student in Maryland. Okay, this whole table is international students, and they're all attending universities in Maryland. So you have 100% chance of selecting an international student in Maryland if you pull from this the members of this table. Okay, so think about the intersectionality. Think about mutually exclusive events and events that overlap, and you'll be successful on this. Thank you for listening.